Good afternoon, friends. We meet after a long gap. Wish you all a very happy new year. To start with, in the last lecture, we had taken one topic, that is bending stresses in beam, and we had derived the bending stress theory. We'll just go through the revision of bending stress theory. The bending stress theory is basically given by the equation m upon I is equal to fb upon y is equal to E upon r, where m is the maximum bending moment in the beam, I is moment of inertia, fb is bending stresses in the beam, y is distance of extreme fiber with respect to neutral axis, E is Young's modulus of elasticity, and r is radius of curvature. So if you want to remember this particular equation, you have to remember it as my phi here, right? That is m upon I is equal to fb upon y is equal to E upon r. This much we had done in the last lecture. Now today we are going to solve certain problems using this particular equation, and then we are going to study section modulus, and we are going to derive the formula for different shapes for section modulus, and then do the numericals based on section modulus. Okay, so this is what we are going to cover in today's session. I've got a session for 2 hours, that is 2 to 4. So we are covering the chapter that is bending stresses in the beam. Right, so we start with the first problem. The first problem says that a simply supported beam is carrying a UDL of 50 kilonewton over whole span. Right, this beam is having a dimension of 150 mm by 400 mm. And if the maximum stress in the material of the beam is 100 Newton per mm square, we have to calculate the span of the beam. So from this particular problem, if we read, then what all is given in this particular problem. First of all, the important is what is the type of a beam. The type of a beam is a simply supported beam. So we have to first write down what is given. So given is simply supported beam. So we can draw a simply supported beam. We know that a simply supported beam has both ends with a support, and this says that it is carrying a UDL of 50 kilonewton per meter. So we can draw a UDL of 50 kilonewton per meter, okay, over whole span. The size of the beam is 150 mm by 400 mm. So the size of the beam, so when the beam is being cut, the cross section of the beam is a rectangle, right? So we can show over here that the cross section of the beam is a rectangle. How do we know that it is a rectangle? So from the dimension itself we can know that it is a rectangle, because it has got B that is equal to 150 mm and D that is equal to 400 mm, right? So we have got the cross section of the beam. Also they have given that the maximum bending stress, that is FB, right? So FB that is equal to 100 Newton per mm square. Find the span of the beam. Span of the beam means what? Span is nothing but the distance between the two supports, and it is denoted by L. So we have to calculate this particular L, right? So this is our total problem in which we have to calculate the value of L, right? Now we know that what is our bending stress theory. So our bending stress theory is m upon I, that is equal to FB upon Y, that is equal to E upon R, right? Now from this particular equation, they have not given us anything regarding Young's modulus of elasticity as well as radius of curvature. So this both equations goes out, and now we have got the equation m upon I is equal to FB upon Y. Right, so now I can use my equation as FB that is equal to my upon I. Okay, so we have to first calculate the bending moment M. So first we have to calculate bending moment M. How we'll calculate the bending moment M? So I will just recall you back. We had studied that if they've given you the standard shapes, standard type of beam, that if it is a simply supported beam subjected to a uniformly distributed load, the maximum bending moment is WL square by 8. If it is a cantilever beam subjected to a uniformly distributed load W, then the maximum bending moment is given by WL square by 2. Similarly, if it is a simply supported beam subjected to central load, the maximum bending moment is given by WL by 8. And if it is a simply supported if it is a cantilever beam subjected to a point load at the free end, the maximum bending moment is called as WL. Right? So in this particular case also we have got a maximum bending moment, and that maximum bending moment can be given as that is it is a simply supported beam subjected to uniformly distributed load. The maximum bending moment will be given by WL square by 8. Right? So maximum bending moment, that is WL square by 8. Now W, we know what is W given, 50. L square we don't know, and upon 8. So we have got 8 4s, 7 8s are 56. 8 6 are 42. 8 6 are 48. Right? So we can say that 6.2 L square kilonewton meters. Okay, so we have got 6.2 L square kilonewton meters as our bending moment. Now from the second diagram, that is from the cross section of the rectangle, what we can find out? We can find out the value of A and we can find out the value of I. Right? So now if I want to find out the value of I, what will be the value of I? I is nothing but moment of inertia. Right? So the second step is moment of inertia. Right? Moment of inertia for a rectangular section I, that is equal to what? BD cube by 12. Right? So B is 150, D is 400 cube divided by 12. So we get the answer as 60 or 80 into 10 to the power 7. What is the unit? Mm to the power 4. Okay. Then we have got Y. What is Y? Y is distance of extreme fiber with respect to neutral axis. So in this diagram, if we see, what is our extreme fiber? This is the extreme fiber, right? Now I have to locate the CG. So CG will be obtained by intersection of the diagonals. So this is the position where CG is located, right? And its distance is D by 2. And from the point where CG is there, the line passes is called as neutral axis, right? So what is Y? Y is nothing but distance of extreme fiber with respect to neutral axis. So Y is nothing but D by 2. So Y, that is equal to D by 2, that is equal to 150, that is equal to 400 divided by 2, that is equal to 200 mm, right? So now we can substitute all the values in our standard equation. What is our standard equation? FB, that is equal to My upon I. Okay. What is the value of FB given? The value of FB is given as 100 Newton per mm square is equal to M. We have calculated as 6.2 L square. Now if you will see, it is in kilonewton meters. Right? So I have to convert in terms of Newton mm because everything is in Newton mm. So 6.2 L square into 10 to the power 3 newtons into 10 to the power 3 mm. Right? So we get as 6.2 L square into 10 to the power 6 Newton mm. Okay? Then what is the value of Y? So the value of Y is 200. And what is the value of I? So value of I we have calculated as 80 into 10 to the power 7 mm to the power 4. Right? So now if I want to find out, we can use our calculators and we can find out the value of L. So 100 into 80 exponential 7 is equal to this divided by 6.2 divided by 200 exponential 6. So that is 8.45. So 8.45 is equal to L square. So L, that will be equal to 8 point root point. So it is 2.90. Okay. So this is the value of the span. Okay. So important is, whenever we are getting any particular problem, then we have to first see what is given. If the beam is given, you can find out bending moment from the loading of the beam, maximum bending moment. If they have given you a section, then from the section we can find out moment of inertia, we can find out area, we can find out y bar. Okay, and then we have to use our equation, that is my phi here. It's a very simple problem, right? Now we take another problem. So the another problem is, again, I have taken a cantilever beam, right? Instead of simply supported beam, I have taken a cantilever beam. Now, why I have taken a cantilever beam? Basically, I just wanted to make you understand that when we are taking a simply supported beam, right? So when we are taking a simply supported beam, what is the type of bending moment? What is the type of bending moment? The type of bending moment is like this, right? That is, beam is bending in this particular manner. So when the beam is bending in this particular manner, then the topmost layer that is subjected, to compression, and the bottom layer is subjected to tension. So now if I have got a rectangular section and if I want to draw a bending stress diagram, so what will be my bending stress diagram? At the top I will have FC, that is maximum bending stress and compression, and bottom it will be FT, that is maximum bending stress and tension. Okay, but suppose if you have a cantilever beam, right? So cantilever beam is in this particular manner. This is a cantilever beam. One end is fixed and another end is hinge, right? And it is subjected to a uniformly distributed, if it is subjected to a point load of intensity W kilonewtons, right? So now what will be the type of moment? The moment will be like this. That means beam will be lifted upwards, right? You can see that the beam has been lifted upwards. So when the beam has been lifted upwards, the extreme layer is subjected to tension, that is at the top, and the bottommost layer is subjected to compression, right? Now in this particular case, if I want to draw a bending stress diagram, then for bending stress diagram, the neutral axis is located by CG. Now what will be the difference? The top will be subjected to tension and the bottom will be subjected to compression. So you have to note that it is which type of a beam. If it is a cantilever beam, then the top layer will be subjected to tension and the bottom layer will be subjected to compression. But if it is a simply supported beam, then the top layer will be subjected to compression and the bottom layer will be subjected to tension. That is why I am taking the second problem as a cantilever beam, right? So now you can read the problem, what the problem is given. So the problem given is that we have got a cantilever beam, and a cantilever beam is having a span of 3 meters and its dimensions are 30 centimeter by 60 centimeter. Okay, so again we can say it is a rectangular section. It is carrying a uniformly distributed load. On the entire span. If the maximum bending stress is not to exceed 10 Newton per mm square, we have to calculate the value of UDL, right? So first and the foremost step is you have to list down what are the data given, because from that particular data it will be easy for you to calculate the values, right? So to start with, suppose we say that they have given you a cantilever beam of span 3 meters, right? So first is given, I will write down the word given so that it makes easier. The span is 3 meters and it is a cantilever beam. So we have to draw a cantilever beam, right? So cantilever beam. From cantilever beam, we can show that it is having, okay, it is having a UDL. So I can write down over here UDL. I don't know the intensity. I will write down W kilonewtons per meter. Okay, and they have given you the span. What is the span? Distance between 2 points, end point and the support, that is given as 3 meters. Okay, second, they have given you a cross section. So we can show that over here we have got a cross section, and the cross section is again a rectangular section. So we are taking a rectangular section. The dimensions are 30 centimeter. So I'll convert it in terms of mm. So it will be 300 mm and 60 centimeter to 600 mm. Okay. So 600 by 300. Okay. So this is given. Also they have given you that the bending stress is not to exceed 10 Newton per mm square, right? So again I'll use which equation? My fire, that is m upon I is equal to fb upon y is equal to E upon r. Now first is I will have to calculate from my loading diagram the value of maximum bending moment. Again it is a standard. What is the standard? Cantilever beam subjected to a uniformly distributed load. So your standard formula is WL square by 2. Okay. Now if you are unable to remember the formula, we know that at free point it is 0 and at support it is maximum. So W into L, that is load, and distance is L by 2, center. So WL square by 2. Okay. W I don't know. So W 3 square, it will be 9 upon 2. So it will be 4.5 W kilonewtons meter. Right? Yeah, I want to convert in terms of mm. So 4.5 W into 10 to the power 3 newtons into 10 to the power 3 mm. So it is 4.5 W into